irrational numbers, decimal representation of rational numbers, period of decimals, and some of the conversions in rational numbers, and some problem based in exercises. Okay, let us move to the irrational numbers here. So as we done the rational numbers before, and we know that rational numbers can be represented as either terminating and recurring with non-terminating. Okay, but here irrational number is nothing but it is either non-terminating numbers or non-recurring numbers. Okay, so for example we have root 2, root 3, Euler's number, that is E, we call it in higher studies you are going to study as exponent. Okay, then we will have a circumference of a circle, we call it pi. Okay. So here root 2, it is a value of 1.4142 and something, it goes on, and root 3 is also 1.732 and so on, like that. And in general irrational number doesn't have any form like rationals. For rational we have p by q. So p by q, where p and q are taken from integers. Also one more condition, it should be a non-zero denominator. Okay, denominator should never be 0. So that is why here we have mentioned q is not equal to 0, and this is a form of rational numbers. And for irrational number we denote q dash or q complement. It is q prefix c. Okay, so q complement or q dash. Got it? So we don't have such forms like rationals, but we do have some of the properties we can also mention in this way, like root of a such that a belongs to prime number. Okay, prime numbers. Or in this way also we can write a does not divide. Okay, a is not divisible by any of even integers, any of even natural numbers. Okay, even natural numbers. Either you can write in this way or this way. Okay, irrational number can be represented as one of these form, not only this form, it is one of this form. Okay, root a is taken as a prime number, or either you can write in this way, a is not divisible by any of those even natural numbers. Got it? Okay, let us move to the decimal representation of q. So before going to look for decimal representation of rational number, I would like to say one more thing. In rational number, see, this is a rational number 0 upon 1 because it is of the form p by q, exactly because see, p and q are taken from set of all integers, and the one more condition is q should never be 0. Okay, it can be integer except 0. Got it? And here it satisfies the condition, these conditions, it satisfies this condition. Also it is of the form p by q itself. See, p is a 0 here. If p equal to 0, it is clearly belongs to integer, and here q is equal to 1. This also completely belongs to integer, and also one more condition, q is not 0 here. Okay, so in this way we can apply for this as 0 divided by 1 is nothing but 0. As you know, this is a obvious manner, because if you put 0 here 1 times, there's only one quotient, 1 times 0 will be 0, and 0 minus 0 is nothing but 0, so remainder will be 0 here, and the quotient is 0. And also if we take reciprocal of this 1 upon 0, this is invalid in mathematics. Okay, we say this number doesn't exist at all, or not defined. In other way we say not defined, but often we call it a symbol as this symbol. Okay, this symbol represents infinity. Okay, we say it either it is not defined or we say it is infinity. Infinity is not a number, it is just a symbol. Like we have set of all integers and set of all whole numbers and set of all natural numbers, capital N. Likewise we have a symbol for infinity. Okay, infinity is not a number, it's just a symbol for not defined. Okay. Okay, let us prove how it becomes infinity. Infinity is a largest number, largest unknown number. Okay. Yeah, we can find 1 upon 0 in this way. So before we going ahead, 1 upon 0 is infinity. We can't say it is equal, it is approximately equal. Okay, let us say 1 is here and 1 by 0.1. Okay, I'm just moving throughout decimals. Okay, so 0.1 10 times 1, so that means we've got 10. Got it? And in the same way, if we proceed 0.001 for 1, your quotient will be 100 and the remainder will be 0. So 1 upon 0.01 is nothing but 100. Okay, in this way if you take on 0.0, how many such zeros you want, you can take that much of zeros will obtain on the quotient. Okay, so and this number is nothing but approximately it is 0 only. Okay, we call it 0 only, but the quotient will be always a huge value, right? So for that such huge value we denote it by the symbol infinity, and thus it is a largest unknown number. We don't know where it truncates or terminates, so that's why it is unknown largest number. Okay, so this way you can have infinity or not defined number. Okay, let us move to the decimal representation of rational numbers. So I'm just moving towards 1 upon 1, 1 upon 2, 1 upon 3, 1 upon 4, 1 upon 5, 1 upon 6 and 1 upon 7. I'm just moving toward this. So we know how to calculate 1 upon 1. So 1 ones are 1 and remainder will be 0. And for 1 by 2, so 2 cannot be a quotient to have such numbers. Okay, so that is why I'm denoting it's a decimal number. Whenever you write 0 point here, 1 0 will add it in your dividend. Okay, so now you can easily divide it 10. Okay, so 2 5 times 10, remainder will be 0. So for this you have 1 and for this one 0.5. Let us collect all those numbers, then we decide whether it is a rational or obviously these are all a rational number because there is no non-zero, there is no zero denominator in denominator. Okay, so what is 1 upon 3 now? 1 3, so 0.033 times 9, again 1, already there is a decimal, so I am giving for 0 here in the dividend. Again 3 times 9, it goes on, I don't know when it is going to end. So for this I am denoting it 0.3 bar. Okay, so bar in the upper side of the number indicates periods of decimals. Okay, here we have only one period of decimals and that is 3. And for 1 by 4, 1 4 0 point, it is 10. So 4 2 times 8, remainder 2, already decimal is there, so 0 4 5 times 20. So this you've got 0.25. Next 1 upon 5 and that is 0.0052 times 10. This is going to be 0.2. I think it is going to reduce, right? So what about 1 upon 6? 0.01 times 6, then 4.066 36, then 0 again, no, 4 again decimal, 66 36, then we have here 0.16 bar. Okay, 16 bar. about 1 by 7? So 0 0.01 times 7, so remainder 3 already 30, so 7 4s are 28, remainder 2 27, 2s are 14, remainder 6 0, so 7 8s are 56, remainder 4, okay, 40, so 7 5s are 35, remainder 5, and it goes on in this way. See, remainder 5 already, 7 7s are 49, remainder 1 till when 10 again 1, so that means 7, remainder 3 again, right? So for remainder 3 we have got 14, so 1, that means 1 by 7 is nearly 0.1428 57 bar. Okay, it will be 4. And for 1 by 8 we can also include 1 by 8. 1 by 8 is 0.125, as you can check, 0.0, so 8 1 times 8, remainder 2 0, so 2 times 16, remainder 4 40, 8 5s are 40, so then 1 by 9, so 0.01 times 9, so 1 point, so 1 1 1, it goes on, okay, so 0.1 bar, and 1 by 10 is 0.1. See, now we can write these numbers are terminating this number is also terminating number, non-terminating plus recurring. Period of decimal, which is 3, it repeats every time, right? So this is a terminating number, and this is also terminating number. This is non-terminating plus recurring, right? So this is also non-terminating and recurring. Terminating, non-terminating, recurring, so terminating. Okay, so these are all the rational numbers which represented in the form of decimals. Got it? We can move to the next. Okay, let us start with the exercise 2.2 here. See here, question is express the following rational numbers into decimals and state the kind of decimal expansion. We need to find two things here. We have to convert in terms of decimals, and we have to find what kind of that decimal expansion which represent rational numbers here. Okay, so as we know, rational number is of two kind. One is terminating decimals. Another one is non-terminating plus recurring decimals. Okay, it may be two kind of decimal expansions. Okay, so let us say this, the given number is nothing but mixed fractions, and this can be converted into, say, minus 11 5s are 55, 55 plus 3 is 58 upon 11. See, the mixed fraction is expressed in terms of rationals. Okay, so not every mixed fraction is a rational number, but every rational number can be expressed as mixed fractions. Okay, it is not converse. Okay, so 11 5s are 55, 55 plus 3 is 58. Now divide this, 11 5 times 55, remainder we have 3. Okay, so if we keep point here, it will be a 30. Then 11 2 times 22, remainder is 8. Then we have 80. 11 7s are 77, remainder 3. Then again 0.030. That means we are going to do 2 times again. That means 2727 is repeating here. Okay, so minus 5.2727 and so on. So this can be written as in this way, and the period of decimal is nothing but 2 here, okay, and it is a non-terminating plus recurring, right? So given minus 5/3/11 is a non-terminating and recurring decimal expansions. Okay, so this is a given number, and for the second one, it is clearly a rational number, but we can solve it. 3 7s are 21, remainder 1.0. So 3 3s are 9, remainder again 1. So point is there. So 3 3s are 9, and I don't know where it's going to end up. So 22/3 is nothing but 7.3 bar, and it is also the same thing which we found in the previous one. And for the fifth one, I think minus 9/32 is given, or fifth question, minus 9/32. See, 9 is 32, so 0.032 2 times, okay, 64. Remaining what you have, 6, 70, 80, 90, that is 26. Already point is there, and 260 will raise up here, and 3 6 are 18, 3 8s are 24, right? So 3 8 times, so that means 32 times 8, and 240 plus 16, 256, yeah, 256, that means 8 times. Remainder we will get 40 again, so this is 1 time 32, remainder 8, and again 0, 2 times 64. It goes on like that, but it is also a, I think it is a terminating decimal or non-terminating. It is one of those kind, but you have to check it, okay? So in this way you are going to find the first problem. Got it? I hope this problem is easier.